The Haber-Bosch process was invented here in Germany more than 70 years ago, but it's only recently that chemists have agreed on the mechanism of the reaction, on what happens when nitrogen and hydrogen react to form ammonia on an iron catalyst. Much of the credit for that agreement is due to electron spectroscopy, a technique that we've come to Munich to learn about. Now, we tend to speak of the catalyst as metallic iron, but it also contains promoters, potassium, calcium and aluminium, all in oxygenated form. But it isn't in the bulk, but at the surface, the reaction site, that the promoters influence reaction rates. So what are their surface concentrations? Well, in here, they can answer that question. So let's go in. This is a scanning Auger microprobe, one type of electron spectrometer that's been especially useful in the study of surfaces. In electron spectroscopy, we persuade the sample to emit electrons. Now, in solid samples, it's only electrons from the upper layers that escape without atomic collisions. Those from the interior beneath are turned back or slowed down. So the electrons from the upper layers have quite distinctive properties, and by studying those properties, we can learn things about the sample's surface. How's it done in this instrument? Well, this is an electron gun. From here, an electron beam is fired down through this housing to the sample at the bottom. The beam induces a particular kind of electronic transition in the elements on the sample surface, an Auger transition, and each element then emits Auger electrons. But for any particular element, those electrons can only have particular velocities, and those velocities can be measured by an electron analyzer stationed above the sample. Well, a sample of our industrial catalyst is already mounted inside here, so let's see what this instrument can do. The area we'll study is selected using a built-in electron microscope. Now the instrument is switched to its Auger spectrometer mode. Here again is the area we're going to analyze. It's tiny, only 1/100th of a square millimeter. The spectrometer's electron beam is focused onto a minute part of this area. The dot leaving a track across the center left of the screen is the point probed by the beam. It's about 1/1,000,000th of our chosen area, only 100 millionth of a square millimeter. Let's call up the Auger spectrum for that tiny point. There are peaks due to Auger transitions in the elements present at the surface. Let's start with potassium. This is one of its Auger transitions. Now the electron analyzer is tuned so that it only picks up electrons with the velocity characteristic of this particular transition. As the beam scans across the surface, the successive intensities reflect the variation in the potassium concentration, and so we can build up a map of the potassium concentration at the surface. In the same way, we can make maps for the other key elements within our chosen area of 1/100th of a square millimeter. This is the map for iron. Here's calcium, aluminium, and potassium again. The brightness is a measure of the relative surface concentrations of these elements. Notice that although the three promoting elements have very low bulk concentrations, their surface concentrations are surprisingly high, especially in the case of potassium. Other experiments show that the promoting elements are all oxygenated. This instrument shows how useful electron spectroscopy can be in the study of catalytic surfaces. Dr. Weiss here did this work when he was part of a research team working with Professor Gerhard Ertl of the University of Munich. During the past 10 years, Professor Ertl's research has made him a world authority on the mechanism of ammonia synthesis. And as I found out, it makes an interesting story. Let's go back to the beginning. Professor Ertl, I suppose that when you began your research on ammonia synthesis, some things were already known about the mechanism.
Of course, it was known that the catalytically active surface was metallic iron, whose activity was enhanced by the addition of the promoters. It was generally accepted that hydrogen undergoes dissociation upon interaction with the surface, so that adsorbed hydrogen atoms were taking place in the reaction. And from the work by Emmett and his co-workers about 50 years ago, it was known that the rate of ammonia formation is equal to the rate of nitrogen adsorption, which means that the nitrogen adsorption step is obviously rate limiting. But here we are running into the first difficulty. Nitrogen may be present on the surface in two different forms, either molecularly adsorbed or atomically adsorbed. And that's why we can formulate two different reaction mechanisms, which I have illustrated on this figure here. The reaction may either proceed through the molecular species, hydrogenation of molecularly adsorbed nitrogen to ammonia, or through the dissociative mechanism where the nitrogen molecule is first dissociated and then the nitrogen atoms on the surface are hydrogenated to ammonia. At this time, it was not possible to distinguish between the different surface species because all the information came from indirect experiments by studying the gas phase, by studying kinetics, or by studying adsorption properties.
So the new techniques, the new surface techniques, opened up the possibility of finding out what was actually happening on the surface.
These new techniques are mainly based on the interaction of electrons or ions with surfaces. They probe the topmost few atomic layers of a solid and can provide us with information on the chemical composition, on the electronic structure, on the atomic structure, as well as on the chemical nature of the adsorbed species.
I see. So how did you begin to tackle the mechanistic problem?
The actual catalyst is a rather complicated system. Its composition is complex and also its structure is not well defined. So it was natural to start with a model system with well-defined surface composition and well-defined surface structure. This was a clean iron single crystal surface.
So Professor Ertl's first work was done on clean iron surfaces cut from single crystals. Because he knew that nitrogen adsorption contained the rate-limiting step, he was soon trying to establish the chemical state of nitrogen adsorbed on iron surfaces. This can be done by X-ray photoelectron spectroscopy. XPS tells us about the binding energy of the core electrons in the adsorbed nitrogen. Because the instrument analyzes emitted electrons, we must make sure that they don't collide with unwanted gas molecules. As in other kinds of electron spectroscopy then, the spectrometer chamber is maintained at ultra-high vacuum, around 10 to the minus 11 atmospheres. The sample is a single crystal of iron sliced to reveal its 111 face. As Professor Ertl mentioned, it has to be clean. The cleaning is done in a side chamber. Here, the surface of the slice is repeatedly bombarded with ions from an argon-iron gun. The bombardments are interspersed with bouts of heating and cooling to even the surface out. This side chamber can also be used when we need to expose a surface to gases near atmospheric pressure. But this isn't necessary in this experiment, so the sample can be moved through a gate into the main spectrometer chamber. Our first spectrum will be run at low temperatures, so we cool the sample to 100 degrees Kelvin. Next, it's exposed to a very low pressure of nitrogen gas, about 10 to the minus 9 atmospheres. After the exposure, the ultra-high vacuum is restored, and we're ready to run the spectrum of the absorbed nitrogen. The X-rays come from a generator above the main chamber. They knock out 1s core electrons from the adsorbed nitrogen. The kinetic energy of the nitrogen 1s electrons is measured by an electron analyzer housed within the spectrometer chamber. This kinetic energy is less than the energy of the exciting X-rays. The difference is the binding energy of the nitrogen 1s electrons. The The spectrometer plots out binding energy in electron volts against the electron intensity. Now, the reason why we performed this experiment at the very low temperature of 100 degrees Kelvin was to create conditions where molecular nitrogen is likely to be adsorbed. So it's probable that this peak is due to adsorbed dinitrogen. But what happens when the temperature is increased? Well, some dinitrogen is desorbed, but that's not all. The peaks moved. This is the spectrum after the surface has been heated to 170 degrees Kelvin. The peak is now at 397 electron volts, not 399. There's been a chemical shift, a change in the adsorbed species. What's the nature of this change? The peak at 399 is probably due to adsorbed dinitrogen. At 170 Kelvin, the species that remains on the surface is clearly not the same. What could it be? Well, the most obvious explanation is that as the sample was heated, some dinitrogen broke down to form nitrogen atoms, and that only these were retained on the surface. If that's right, then the adsorbed monatomic nitrogen must be especially strongly held, because the peak we see at 170 K still persists even when the surface is heated under high vacuum to 700 degrees Kelvin. To test this idea, Professor Ertl looked at the compound Fe4N, iron nitride. He found that its nitrogen 1s spectrum contained this same peak at 397 electron volts. Now, the structure of Fe4N is known. Here's the unit cell. It contains a single nitrogen atom, monatomic nitrogen. So here's evidence that the signal at 397 electron volts is due to monatomic nitrogen bound to iron. Above 100 degrees Kelvin, then, nitrogen adsorption is dissociative with an adsorbed molecular precursor. The final product, the monatomic nitrogen, is especially strongly held. This tells us that even at the temperature of industrial ammonia synthesis, monatomic nitrogen is prominent on the catalyst surface. How can this help us to distinguish between the associative and dissociative mechanisms?
It turned out that the study of the atomic nitrogen species provided us with a key for resolving the mechanism of this reaction. In fact, its concentration is crucial for this whole problem. Let's go back to our reaction scheme. We have seen that nitrogen can be molecularly adsorbed, and it can also be dissociatively adsorbed on the surface. Now let's assume for the beginning that the reaction would proceed through the associative mechanism, this route here. Since we know that the molecularly adsorbed species also undergoes dissociation, we would also build up atomic nitrogen on the surface, and since this species is not removed in this case, it would necessarily build up to saturation on the surface. If, on the other hand, the reaction would proceed through the dissociative mechanism, the atomic species would be formed in this step, and it would be removed through the subsequent hydrogenation reaction. And as a consequence, the steady-state concentration of atomic nitrogen should always be below the saturation value.
So we have to measure the steady-state surface concentration of monatomic nitrogen while ammonia synthesis is actually going on. Now, earlier, we used Auger spectroscopy to follow concentration changes across a surface. So we use Auger spectroscopy again. But first, we have to calibrate the spectrometer, and for this we need low-energy electron diffraction. Professor Ertl built both these techniques into one instrument. In a lead experiment, we fire electrons at the surface and study the pattern of the diffracted electrons. At the moment, the instrument contains a clean iron 100 surface. Its structure is based on a simple square lattice. To start the experiment, the sample is turned to face the lead detector, here at the back of the spectrometer chamber. The diffraction pattern, like the surface lattice, is also a square array. The next step is to saturate the iron surface with monatomic nitrogen. A prolonged exposure to nitrogen gas will do it. About 10 to the minus 6 atmospheres for 12 hours at 600 degrees Kelvin. Now, has the lead pattern changed? New spots have appeared. This new pattern bears a simple relationship to the old one. The relationship tells us that the unit cell of the adsorbed nitrogen atoms is centered, with a side twice that of the unit cell of the iron 100 surface beneath. Now, how many nitrogen atoms does the surface nitrogen unit cell contain? 1 and 4/4, 2. And there are also 4 iron atoms within the bounds of the cell. So on the saturated surface, there will be 2 nitrogen atoms to every 4 iron atoms, a ratio of 1 to 2. To complete the calibration, we simply turn the sample to face the electron beam of the Auger spectrometer. Now we can run the Auger spectrum of the nitrogen-saturated iron 100 surface. Here's the spectrum. These signals up here come from iron. I'm going to concentrate on the middle one at 650 electron volts. Down here at 380, we have a signal from nitrogen. You can see that these 2 peak heights are similar. So on this saturated surface, where the nitrogen-iron ratio is 1 to 2, the ratio of these 2 peak heights is close to 1. Now we can use this calibration of the Auger spectrometer to determine the surface concentration of monatomic nitrogen during ammonia synthesis. But there's a problem. Auger spectra have to be recorded at very low pressures, less than a millionth of an atmosphere. But to get detectable formation of ammonia over iron, the pressure will have to be very much larger, about 1 atmosphere or more. This is a difficulty we always meet when we apply electron spectroscopy to catalytic problems. It's called the pressure gap. How can we get round it? Well, we can use a side chamber to perform the reaction at atmospheric pressure, then transfer the sample to the high vacuum spectrometer chamber. But can we be sure that it isn't affected by the pressure change?
Our reaction was performed in the temperature range around 300 degrees centigrade. And of course, it's now necessary to look at the thermal stability of the different surface species under vacuum conditions. And this is listed in this table here. Hydrogen, which is dissociatively adsorbed, desorbs already below 200 degrees centigrade. The molecularly adsorbed nitrogen species is very weakly held. It desorbs already below minus 100 degrees centigrade. The adsorbed ammonia molecule also desorbs below around 100 degrees centigrade. But the atomically adsorbed nitrogen species, which we are interested in, is so stable that it recombines and desorbs only at temperatures above 450 degrees centigrade. So if we are working at 300 degrees centigrade, it's quite obvious that the concentration of the species we are measuring under high vacuum conditions is identical to the conditions we have established before under our steady-state reaction conditions.
Yes, I see. So you measured the surface concentration of atomic nitrogen under reaction conditions. What did you find?
Let's look back at our Auger spectra. First of all, the spectrum from the nitrogen-saturated surface, and you see that the signal from the nitrogen is comparable in magnitude to that of this iron signal. If we now do the same experiment with a surface which was exposed to a reaction mixture, we get a spectrum as shown here. And the relative intensity of the nitrogen signal is now much smaller, so we know for certain that the concentration of the nitrogen is far below saturation. This brings us back to our question of the reaction mechanism. We have now demonstrated that the concentration of the atomic nitrogen species is below the saturation value, and this excludes the associative reaction mechanism. We have thus demonstrated that the reaction proceeds through the dissociatively adsorbed nitrogen, which is then hydrogenated. If we look at this reaction sequence, it also becomes obvious that the concentration of this atomic nitrogen species should be affected by the rate of the subsequent hydrogenation reaction, which in turn can be affected by the pressure of hydrogen. So if we measure the nitrogen concentration on the surface as a function of hydrogen pressure, we would expect that this concentration decreases with increasing hydrogen pressure. And this was in fact also observed. This figure shows that the concentration of atomic nitrogen as a function of hydrogen pressure at constant temperature and constant nitrogen pressure, and we clearly see that the concentration of atomic nitrogen continuously decreases with increasing hydrogen pressure. This point in fact marks the situation where we have a stoichiometric mixture, and we see that under these conditions the concentration of atomic nitrogen on the surface is far below the saturation value. And if we now go back to our reaction scheme, that means that under steady state conditions the concentration of atomic nitrogen on the surface is fairly small, and as a consequence we have to conclude that the rate of this first step, the formation of this species, is slow. This confirms our idea that the dissociative adsorption of nitrogen is a rate limiting step. Now if we look into this reaction in more detail, it turns out that it is composed of two steps: the formation of the molecularly adsorbed species and the dissociation of the latter. Independent studies revealed that the first step, namely the dissociation of the nitrogen molecule, is slower than this step here, the adsorption of the molecular species. And also desorption of the molecular species is a rapid process, so that we have in fact a pre-equilibrium from where the reaction goes on. So the dissociative adsorption of nitrogen is a rate limiting step for the overall reaction.
But we've yet to get to grips with the industrial catalyst. So far we've only studied the mechanism on pure iron surfaces, yet we know that at the surface of the real industrial catalyst other elements are every bit as prominent as iron. So how is the synthesis of ammonia encouraged by the promoters, the potassium, calcium and aluminium? Let's go back again to our scanning Auger maps. Let's add calcium. Now, aluminium. By and large, these elements occupy the gaps in the iron map. They act as structural promoters, keeping the iron crystallites apart, stopping them from sintering. Aluminium is also finely scattered throughout the iron surface, suggesting an especially intimate role as a structural promoter. Potassium is quite different. It occurs wherever the iron is, and at even higher surface concentrations. But the two elements are not freely mixed, as these maps might suggest. Now this instrument is equipped with an argon-iron gun, which can progressively remove surface layers. When we do this, we find that the potassium disappears almost at once. This shows that the potassium forms a very thin layer over the top of the iron surface. Now in ammonia synthesis, the iron surface is the center of catalytic activity. That's where it all happens. Yet here, an element which covers up that surface actually encourages the reaction. How can this be? This problem too is one which electron spectroscopy has helped us to solve. But for the answer, you must turn to the course unit text.